Hi, today I want to show how you can deal with the redundancies in a rigid body simulation or NX motion. Here I have a simple example to show what does it mean to have a redundant joint and how you can deal with it. Now consider a door like this. To hold the door, you basically need to eliminate all the degrees of freedom except the rotation around z-axis, which means that you need to use a hinge. So let's say you use the revolute joint to basically eliminate all the degrees of freedom except the axial or rotational on the z-axis. Now, if you do that in reality, that joint is going to carry a lot of torque because of this load of the door being applied on the joint one. So in practice, you add more hinges on different places, so the load is being distributed on all of them. But again, you only need to have one degree of freedom, which is the rotation around the z-axis. And adding more joints is not going to help more with that rotation. As a result, the software is going to ignore any other joint that is trying to apply the same constraint to the system. So for the joint one in this example, what we can do is to make the joint more flexible. And as a result, it can carry the load according to the flexibility of it. In this case, we want to have a joint that is radially stiff, meaning that it's radially flexible, and conically compliant or compliant in torsion as well, and longitudinally or axially stiff as well. So it can't move up and down, can also move on the y-axis and x-axis, and can only rotate around the z-axis. If we do that for all three joints, then all of them are going to carry the load or the torque in different directions. So basically, they're going to share the force if they have flexibility. But if joint one is rigid, there isn't any load that is going to be distributed to other joints. The rigid joint is going to carry all the load because it won't allow for any deformation. But if we put a bushing, that will make it flexible, and that will deform, and the deformation allows the other joints to carry the force as well. Now you can define this kind of freedoms in different coordinate systems. It could be a general Cartesian coordinate system or a cylindrical or spherical coordinate system. Here is what is NX is using in spherical coordinate system, and these are the meaning of each one. So let's move to NX and see how it actually works. I have an example here that I already solved. Uh, there are two hydraulic cylinders that are moving the bucket down, and as a result lifting the excavator up. Now as you can see, I have defined two pins here, a boom pin left and right, and you can already see that one of them is going to be redundant, and in such a big system like this, it's usually difficult to find all the redundant joints, but an easy way to find that is to just check this Grubler count. And the Grubler count is 6 per motion body. And every degree of freedom you constrain, you reduce that Grubler count by 1. So if the Grubler count is negative, that just shows that the system is over constrained. And if it's positive, that shows that the system is under constraint or you have falling parts or loose parts. When you solve the system, you also see more details of the redundant constraint. It specifically shows the name of the type of each redundant constraint. This is not an error or a warning. It just shows that you have joints that are going to be ignored in the simulation. Now let's focus on these two cylinders because I actually want to extract the forces for the cylinders because I want to design screws for sealing these hydraulic cylinders. To extract the force, you just move to that joint, you click on it, you go to XY result view, and then it will allow you to extract any kind of load that you want. Let's extract the magnitude of force. And on cylinder 1, the force is around 1,000,000 Newton. And if we extract the same force relative force magnitude, you see comparing to cylinder 1 is nearly zero. This is the cylinder 1 is around 1,000,000 Newton while cylinder 2 is carrying around 6,000. So you see that the cylinder 2 is actually being ignored and it's not carrying any load, except of course the gravity force only, which is this 6,000 Newton. But the other joint is transferring all of the force to the cylinder, and that's why we are seeing the maximum force on that. In reality, both cylinders should work together to lift the excavator. So let's see how can we fix that. Basically, to make the joint flexible, first we need to remove the pin joint or the revolute joints and replace them with bushings. So I deactivate these two pins, I move to home and I define bushings between the cylinder and the boom instead of the pin that is now deactivated. I select the motion body as this ring and the base as the boom. The boom is one body and the cylinder head is one body. Make sure you correct the origin. The origin should match the origin of the corresponding pin that you had in the simulation. For this, the origin is in the center of this ring here. I'm gonna move it between 2 points to pick that up. Also, I want to change the coordinate system so it's easier to read the loads. The z-axis is now the axis of the pin. And I click apply. Now, if I go down on the connectors, you're gonna see a new connector is added there. I'm gonna do the same thing for the other side, the base, and then I'm gonna fix the origin between 2 points. And the coordinate system. And click OK. Now let's go back and fix the stiffness parameters. Here in the top you see it, you have a stiffness, damping, and actuator. If I move to a stiffness, you see the same coordinates that I've shown here. So for this system, I selected cylindrical because it resembles a pin. But you could go with a general type of bushing, then you're gonna have all the degrees of freedom separately, both transition and rotational. You're gonna have a spherical as well and as cylindrical, but in this case, cylindrical makes more sense. So what I want to do is to define a stiffness for each degree of freedom. Instead of having a rigid joint, of course. Usually for stiffness and damping, you're gonna try different numbers that generates the best results for you and makes more sense. And the actuator means that you're gonna have an initial movement when you start the simulation, which I don't have here. I click OK, I'll move to other one, and for the other one, I just need to copy. So I can use this inherit coefficients here and select the first one. This way, we'll just copy everything from the other bushing to the next one. Now let's save here, and I'm gonna solve. And you can immediately see the Grobler count dropped because we actually made some flexible joints in the system. Now let's go back and check the forces on cylinder 1 and 2 again. So I go here, relative force magnitude, and I'm going to have it in the same graph. This is for cylinder 1, and for cylinder 2 I go to force and force magnitude. So now you can see that the initial jump is where the simulation starts, and you have a very fast convergence. This is because the boom basically drops to this cylinder ring at the start of simulation, and then it starts to converge to the some number, which is basically the weight of the boom. And I can you can see that this is basically equal. Cylinder 1 and 2 are now equal and around the converging to a million Newton. While in the first simulation, all of that was being carried by cylinder 1, but in the case number 2, which we made the bushings, now two equal 1 million Newton are being distributed on both sides, and can now play and see the result. Basically see the same behavior, but now the numbers make more sense.